All right, good morning. So this is the fourth lesson on energy, 4 out of 5, and it has to do with temperature, heat, and thermal energy. So far we've gone over work, power, conservation of energy, which deals with kinetic energy and potential energy. And then last day was looking at something called mechanical advantage and efficiency of different simple machines, most likely levers or pulleys. All right. So when we start this lesson, there's something called the kinetic molecular theory, which is a very famous theory, which says that all materials are made up of tiny particles, which are always rotating, translating, and vibrating. Okay, so rotating is, if you can picture, say, this piece of paper here, which is trillions of tiny atoms. All of them are moving around slightly, but they're all connected to one another. They're all attracted to one another, but they're all slightly moving, but we can't see it with our own eye. So that's this theory, is saying that that is a thing. There are tiny particles which are always rotating, which means each circle or atom kind of rotates like that. Translating, which means they move kind of side to side, and vibrating, which means they kind of shake. Alright, so all you have to know for this is things are always moving, and that kind of makes your thermal energy slash heat slash temperature. Okay, so this paper right now has a certain temperature. It's probably around room temperature, 20 degrees Celsius. So the atoms in it are moving at a certain rate. As the room temperature gets hotter and transfers its heat to this paper, then the atoms will move faster. And if it got colder or you stuck it outside, the atoms in this paper would move slower. Okay, that's kind of the theory, is movement of a material or atoms of a material. And everything has this. Alright, so overall they say there's 3 definitions. Thermal energy is just the total energy of all the molecules in a material, or kind of that movement energy that they have. So it's kind of hard to measure, but it's just the total energy in a material. I wouldn't worry too much about that one. Heat definition is the amount of energy being transferred from one material to another, right? So right now, if I stuck this piece of paper inside a ice bath, some of its movement energy, its thermal energy, would move into the cold bath, and therefore the paper would get colder and the bath would get a little warmer. You probably wouldn't be able to even feel the temperature difference, but the amount of thermal energy or movement energy that transferred to the bath is called heat. It's just the transfer of that energy. And really the transfer is just the movement of the particles in the paper would bump into the water molecules, causing those to move a little faster. Okay, and these bumping into that would cause the paper molecules to move slower. So heat is just the transfer of this movement energy. Okay, so really thermal energy and heat is just movement. That's all it is when you're thinking about it in kinetic molecular theory. Last of all is there's temperature. We all know what that is. You stick a thermometer in something and you can find out the temperature of it is. And technically, you would say it's measuring the average translational kinetic energy in a material. So it's saying how hot something is. Okay? So if you have something at 100 degrees Celsius, that means if you took an average of all the atoms in that material, it would be the average speed that they're moving at. Okay, the higher the temperature, the faster they're moving at. Alright, and that brings us to these 2 units here of temperature, of measuring temperature. We all should know, I think, Celsius which is a unit of temperature where 0 means it freezes water, doesn't freeze everything, just water. 100 degrees boils water, and negative 273 degrees Celsius is the absolute zero. So what that means, absolute zero, means you cannot get below a temperature of negative 273 degrees. That is the coldest that it will get, which is pretty interesting. You can see 0 and 100 are nice numbers. That's how they made Celsius. That's how they defined it. They said 0 freezes water and 100 boils water. That's how they made it up. So that's Celsius, and we're going to use that. Kelvin is interesting. It uses the same exact increments as Celsius. So 1 degree Celsius increase is the same as 1 Kelvin unit as well. So a unit of temperature, but this time it's saying 273 freezes water, 373 boils water, and 0 is the absolute zero. So when you're using Kelvin, you can't go below 0. So everything's going to be a positive number. So in sciences, they use Kelvin quite often. They also use Celsius, but you don't really see Fahrenheit. All right. Sample questions. Why is it incorrect to say that a body contains heat? Well, if we look at the definition, heat, the amount of energy being transferred to another material, always hotter to colder. Can you contain transferring material? Not really, because it's transferring. So you can say because heat is the transfer of this thermal energy, so if it's transferring, it doesn't contain it. Okay, so that would just be a technical question. Question 2. A large pot of near boiling water, draw the pot right there, with the water in here near boiling, which means it's close to 100 degrees Celsius, has a red hot nail dropped into it. So I'm going to drop this hot nail into it. If you kind of talk about chemistry a bit, every material has different boiling and melting points. It means that every single material has their own certain specific number which will melt it, and a higher number which will boil it. Okay? Water is unique as their nice numbers. So 0 degrees melts water, or melts ice into water, and 100 degrees boils it into water vapor into the air, or a gas. So this nail, generally all metals have really high melting and boiling points. So a red hot nail is dropped into it. So it says which one has more thermal energy. So if I look to the definitions, thermal energy is the total energy of all molecules in an amount of material. Okay, so it's kind of hard. They don't really give you value, so it's not a perfect answer. But if I look at 1, I would say the water has more thermal. And the reason, because of this, the nail might have a higher temperature. It probably does. But the water, there's more of it. Okay, so if you have tons of kind of normal moving molecules, or 100 degrees is pretty fast, so they're moving pretty fast, tons of those, versus the nail where they're moving really fast but there's very few of the molecules. Overall, the water will probably have more thermal energy because more of it. So thermal energy takes into account how much there is as well. Question 2. Which has higher average kinetic energy to begin with? So in this question, it really just means which one has the higher temperature. They don't really give us that, but overall I would assume the nail has a higher temperature because it has a much higher melting point or boiling point. So if it's red hot, that generally means it's a really high temperature. So the red hot nail has a higher temperature. All right, question 3. Which will lose heat? Which one will gain heat? Well, if the red hot nail has a higher temperature, it will lose temperature, and if the water has a lower temperature, it will gain that temperature. Okay, so it always goes from hotter to colder temperature. So a nail will lose heat. And when you talk about heat, it's really just energy. So I know we worked with joules. That's the same unit that they use to define heat or temperature, or thermal energy, sorry, is how many joules something is being transferred or have. And last of all, if I draw this pot again with the handle, they have this word called conduction. You might have heard it in Science 10, which is the transfer of heat from molecule to molecule through material. So this handle, again, has little tiny atoms everywhere, very, very small. And conduction means if you heat up one side, the molecules will move and they'll bump into the ones next to it and cause those to move more. And then they'll cause the next ones to move down. So it's heat moved through a solid. So it's kind of like a solid heat movement. Okay, an example is when you have your coil underneath your pot and it heats up the metal of the pot all the way around, but it'll start off from the heat source. Okay, that's conduction, and generally metals have fast rates of conduction. Alright, and then the next one is convection, transfer of heat movement through liquids and gases, where hot rises and colder sinks. So an example here is through conduction your metal will get hot, which will bump into the water, which will cause, through conduction, the first one, the water to heat up, and that'll cause it to eventually boil. But once, say, it transfers to this water will get hotter down here, and then convection will happen. So when it turns into a liquid or a gas, that's when you call it convection, and it's where the hot water will start to rise up, and then the colder water on the top will go down, but then the colder water will get hot because it's close to the element, and it'll cause kind of this current, convection current, where it heats up. So it's just liquids, gases. A good example is a furnace in your house. When it's moving air, it'll heat up the air, which will cause hot air to rise and the colder air to sink, and then it'll cause some sort of current or convection current due to your furnace heating up the air. Last of all is radiation. This is the transfer of heat through electromagnetic waves that you can't see, and it's from the sun mostly. Okay, so generally if you see radiation word, it just means the heat from the sun. And it can come from other things. There's radiation that comes from kind of everything, but the sun is the main source that we really talk about. Alright, so that's our kind of our first page of theory. Now we can go to some interesting calculation problems. Alright. So here, specific heat capacity is the amount of energy needed to raise 1 kilogram of substance by 1 degree Celsius. So this is kind of the main word for this lesson that you want to get, is specific heat capacity. So it's very interesting, and this is the equation that we're going to use for everything, is delta E equals mc delta T. Delta E is change in energy. It's your energy final state minus your energy initial state. But you don't really use that at all. Your mass is your M, and this is always in kilograms. Make sure it's in kilograms. Specific heat capacity value is this new variable C. Okay, it's kind of similar to a calorie actually, but you can see I have a chart here of a whole bunch of different substances, and they have a whole bunch of different specific heat capacities. Okay, and what unit they're in, this is the unit that it has. This is this fancy one called joules per kilogram per degree Celsius. It's synonymous with joules per kilogram degree Celsius, written like that over just one division. So these two things are the exact same thing. If you can make two division symbols, or you can make one, and it means the same thing. Joules per kilogram degree Celsius, or it means joules per kilogram per degree Celsius. Same thing. You can see water's at the high end of the chart and lead's at the bottom end of the chart. So here, that's our specific heat capacity value. So what it means is it takes 4,200 joules of energy to raise 1 kilogram of water by 1 degree Celsius. Okay, that's a really high amount of joules to heat up. Water is a very special thing as it has a really high specific heat value. If you go down to the other end, you have lead, which only takes 130 joules of energy to raise 1 kilogram of lead by 1 degree Celsius. So lead is very easy to heat up. It doesn't take a lot of energy. Water takes a crazy amount of energy, way more than everything else, to heat up. Okay, that's why it works as a really good coolant in your car, because it can take a lot of that energy and not heat up very much. The change in temperature, that's what that means. And it always is TF minus TI, your final temperature minus your initial temperature. That you use a lot. And last of all, change, or the triangle, just means your final state minus your initial state. That's what the triangle really means. That's why energy has it and temperature has it. So let's look at a question to see what they look like. How much heat is needed to raise the temperature of 90 kilograms of water from 18 degrees Celsius to 80 degrees Celsius? So you always start these questions with your equation. Change in energy is equal to mass times specific heat capacity times temperature. Okay, so it says how much heat, which means how much energy. Our mass of water is 90 kilograms. Specific heat capacity, you look at the substance as water, and then you look at your chart. Your chart is 4,200. So that's our C value. 4,200 is the water one. And then change in temperature, which is always TF minus TI. Your final temperature minus your initial temperature is 80 minus 18. So overall, that's delta E equals 80 minus 18 is 62. And then we go 62 times 4,200 times 90. And this will give me 23,436,000 joules. Joules because it's energy. So it'll take 23 million joules to heat up 90 kilograms of water, which is 90 liters of water, by 62 degrees. It's a lot of energy. Okay, so you can assume your water heater needs a lot of heat or a lot of energy to heat up, and that is true. And that's generally why you might use up all the hot water, and it'll take a while for you to get it back. If 25,000 joules of heat, or 25 kilojoules of heat, is transferred to 50 kilograms of water initially at 20 degrees Celsius, what will the final temperature be? Okay, again we go delta E equals MC delta T. The change in energy is equal to the mass, specific heat capacity, and the change of the temperature. So this time they give you a kilojoule value, so you know you're going to have to use that for energy. So 25 kilojoules is 25,000 joules. Our mass is 50 kilograms. Our specific heat capacity of water is 4,200. If we look at the chart, a lot of these questions will use water because that's kind of the most common thing that you'll use this for. And then last is TF minus TI, or because that's what the change in temperature means. So we have 25,000. Let's do that calculation. 50 times 4,200 is 210,000. And our final temperature is what we're trying to find. And our initial temperature is 20 degrees. So let's do a bit of algebra. We'll distribute this on the inside. So we have 25,000, 210,000 times TF, and then 210,000 minus 20. And we get negative 4,200,000. All right, now we got to solve for TF. So we'll add this to the other side, and we'll get 25,000 plus 4,200,000. and I'll get 4,225,000 equals 210,000 times TF. And now we divide by 210,000 onto the other side, and we'll eventually get TF. Let's do that. Divisions. 20.1 degrees Celsius. So overall it takes 20.1 degrees Celsius, or not, our final temperature will be 20.1 degrees Celsius from 20. So we're putting in 25,000 joules of energy, which is a lot, and our water will only increase by 0.1 degrees Celsius. Interesting. Water is interesting. Okay, our last question is 3. If it takes 1,200 joules of energy to raise the temperature of half a kilogram of brass this time, from 20 degrees to 26.2 degrees, what is the specific heat capacity? You always start with the equation. Change in energy is 1,200 joules. Our mass is half a kilogram. Specific heat capacity of brass, we actually don't know. It's not even on our chart. So we're just going to leave it as C. Change in temperature is 26.2 from 20. So you just minus the 2. And you get 6.2 is the change in temperature. We have to solve for C, so divide by this, divide by that, and we'll end up with a C value of 387.10. And what unit does C have? Let's look. Joules per kilogram degree Celsius. Joules per kilogram degree Celsius, what does that mean? It'll take 387 joules of energy for brass to heat it up. To heat up 1 kilogram of it by 1 degree Celsius. So if you have more kilograms, it'll take more energy. If you have more temperature to increase to, it'll take more energy. Thank you.